It's now my pleasure to introduce Dr. Stephie Fried, who I think has traveled all the way from Arizona. She has. She's now at Arizona State University in the Carey School of Business. She has her PhD from University of California, San Diego. Now, fascinatingly, her research focuses on the environmental impacts and implications for the macroeconomy, but put this in a context for us today, she gives us insight about the value of climate adaptation, this fascinating question of what are the impacts as we try to figure out how to adapt, and look at the actual FEMA programs. FEMA has two programs. They have an assistance program after disaster hits, but they importantly have a mitigation program, mitigation planning program, which is supposed to help communities be stronger or be prepared or be more resilient to that action. So again, it's my great pleasure to introduce Dr. Fried.
Thank you very much for having me and for putting together this meeting. So I want to start by defining what I mean by adaptation for the context of this paper. So this is going to refer to any capital whose specific purpose is to reduce the damage from extreme weather. And by extreme weather, what I really have in mind are storms. So this picture on the left is part of the system of flood barriers and seawalls surrounding New Orleans. This could be a very big and a large-scale capital investment that we count as adaptation. It could also be a much smaller scale capital investment done by a house. So this is a house that's been raised up on stilts to prevent flood damage. There, the adaptation is not the entire house, but just that extra capital necessary to put it on stilts to reduce the risk of flood damage. So what I'm interested in are two questions. First, I want to understand how U.S. federal disaster policy affects adaptation incentives. And so you can think of federal disaster policy as having two prongs. So first, we provide aid for disaster relief, and that's primarily through FEMA. And then second, we provide subsidies for investment in adaptation. And those subsidies come from several sources, mainly through FEMA and the U.S. Army Corps of Engineers. Now this FEMA aid for disaster relief reduces the kind of net cost of a disaster to a particular area because the government compensates them for some of their losses. And so what that means is that could then in turn reduce that area's incentives to make investments in adaptation. So there's this sort of what we think of as a moral hazard type effect, or potential for a moral hazard type effect from FEMA aid. The federal government knows this, they seem to know this, and so they also introduce these subsidies which are designed to counteract that moral hazard effect because they reduce the relative price of adaptation. So if I want to put my house up on stilts, maybe FEMA will pay 75% of the cost, I'll only have to pay 25% of the cost. They make it cheaper for me, and so they increase the amount of adaptation I do. So what I'm interested in here is first, how big are these moral hazard effects from FEMA aid, and then how effective is the subsidy at offsetting that moral hazard. And then the second question is to think about adaptation in the context of climate change. And here I just want to focus on one specific type or predicted outcome of climate change, which is an increase in the severity of extreme weather, of storms. And I want to understand first, how much does adaptation respond to this type of climate change? And then how does that adaptive response affect the damage and the welfare costs from the climate change? So to do this, I developed a general macro-style model of adaptation investment. I'm going to show you the model in a picture, then I'll give you just a tiny bit of the math, and then we'll go to the results. So what you think about is dividing the U.S. up into n different regions, where these regions are different based on their distributions of extreme weather. Again, these are storms. Then so inside each region, we're going to think about there being a continuum of heterogeneous localities. So think of these as counties, lots of counties within a region. And then all of these counties or localities are going to be ex ante identical, but they experience different sequences of extreme weather shocks. And so some periods, some are hit by a storm, other periods, others are hit by a storm, and so on. These counties are all run by local governments or local social planners that make decisions to maximize the welfare of the representative household living in that county. Now that planner or local government can choose three things. First, She can decide the county's level of productive capital. This is what we normally think of as capital, your buildings, your factories, your machines. It's what's used to produce output in the particular county. Second, the planner can also decide that level of adaptive capital. These are your seawalls, your stilts, your storm drains that are reducing the damage that county experiences if she's hit by a storm. And then third, the planners can purchase insurance, things like homeowners insurance or flood insurance, that reduce kind of the risk that the county faces given that there are these extreme weather shocks. And then presiding over all of this is the federal U.S. government, which taxes all of these localities and then uses the revenue basically to finance U.S. disaster policy, so to provide that FEMA aid for disaster relief and the subsidies for adaptation. Okay, so just a small bit of the map. The way this is set up is each period, at the start of the period, the extreme weather shock realizes. So if epsilon equals 0, you don't, there's no storm in your county. If epsilon equals 1, you're hit by a storm. And P is the probability that you'll get hit by a storm. And this probability is allowed to vary across those different regions in the US. Then if you are hit by a storm, this destroys some of your productive capital stock. So think about a hurricane coming through and destroying your buildings, your factories, and so on. So K superscript P here is the productive capital in a particular locality. KD is the capital that was damaged by the storm. And the subscript here, I is your region, and then J is the locality within that region. And if we walk through the pieces a little bit of this equation, omega is telling you the severity of the extreme weather in that region. So what fraction of your productive capital stock is destroyed if you get hit by a storm. And this is also going to be allowed to vary across regions. So those regions of the US, again, are differentiated based on the probability that they get hit by a storm, and then by how bad the storm is if it does occur. KA is the locality's stock of adaptation capital, so how many seawalls and stilts and so on it has. And H of KA is a function that translates that stock of adaptation capital into reductions in damage. So importantly, this function is decreasing in the level of adaptation capital. So as I have more seawalls and more stilts, this reduces the damage I get if I'm hit by a storm. Now, an important parameter that we're not going to have time to talk about is this parameter theta, which is basically determining the effectiveness of the adaptation. And this is going to be very important for the quantitative results, and so I just want you to know that this does come from at least empirical evidence on the data on disasters. So turning next to our results. So we're going to run 2 experiments in the model, one for each of those questions. So first experiment is to look at the effects of federal policy. And so I'm going to compare 3 different equilibrium in the model. The first is what we'll think of as our baseline equilibrium. This is, you should view as kind of the US economy today. And it's basically, we have all the elements of federal disaster policy that we have in place. So with the FEMA aid and with the subsidies for adaptation. Then we'll look at 2 counterfactual equilibrium. In one of those equilibria, I'm going to get rid of all federal disaster policy. So there'll be no FEMA aid and no subsidies. And then in the other equilibrium, we'll have the FEMA aid, but there will be no subsidies. And comparing these different equilibria will let us quantify the moral hazard effects from FEMA aid and the effectiveness of the subsidy at offsetting those moral hazard effects. And so what we see here is this graph is showing you adaptation capital as a percent of the total U.S. capital stock in the counterfactual equilibrium in which there's no federal disaster policy. So this says if we get rid of the FEMA aid and the subsidies for adaptation, then adaptation capital would be 0.04% of the U.S. capital stock. Now I want to compare this value to what happens when we introduce the FEMA aid, but we don't bring in the subsidy. Then that moral hazard channel says FEMA aid means the areas are experiencing, basically reducing the cost of extreme weather to an area that reduces their incentives to make adaptation investments, and so we should see adaptation capital fall. And so we do. In this case, it goes all the way to 0. It didn't stop there. And now we say, okay, well, this is not what the federal government's done. They provide this aid for disaster relief, but they also have this subsidy, which reduces that relative price of adaptation investment, makes it cheaper, so it should offset some of this moral hazard effect. So when we add back in the subsidy, we should see adaptation go higher than the aid-only equilibrium. If that subsidy perfectly offsets the moral hazard, then we would see adaptation capital equal the value in that no policy equilibrium. Instead, what we see is that adaptation capital is actually a lot higher than in the no policy equilibrium. And so what this means then is that the net effect of U.S. federal disaster policy is actually to increase adaptation capital in the U.S. economy. I want to comment for a minute on the size of these numbers. So what this purple bar says is that adaptation capital is 0.13% of the total U.S. capital stock. It seems small, but if you then compare this to the amount of the U.S. capital stock that's destroyed by storms each year, that's about 0.23%. So what this says is that adaptation capital is about over half of the total capital that's destroyed by storms. Now the second experiment is to look at the effects of climate change. And again, focusing on just one type of climate change, which is that increase in storm severity. So we'll model this as a permanent increase in that severity parameter. And I want to think about three different climate change scenarios. A 50% increase in storm severity, 75, and 100% increase. And again, I'm going to compare several different equilibria or steady state. So we'll have the same kind of baseline equilibrium. You could think of this as the U.S. economy today, or the no climate change equilibrium. And then we'll calculate two different climate change equilibrium in which we scale up that severity parameter by some factor depending on the scenario. In one of those climate change equilibria, we will let adaptation adjust. So we'll just resolve the whole model with a higher value of the severity parameter and look at how adaptation responds to that increase in severity. In the other climate change equilibrium, we're not going to let adaptation adjust. We're kind of going to artificially fix the level of adaptation capital at its value today in the U.S. economy, and then we're going to resolve the model. And then basically comparing those two equilibria will let us understand how much adaptation affects the damage and the welfare costs from climate change. So what this graph is showing you on the x-axis is the scenario, so the percentage increase in storm severity, 50%, 100, 75%, and 100%. And then what I've plotted here is the percentage increase in damage relative to our world today, to the baseline. So in the case where there's no adaptation, so we can't adapt, the adaptation capital is fixed at its value in the today. If there's a 50% increase in storm severity, this would lead to almost a 50% increase in damage. It's not a full 50% increase because there's some changes in the productive capital. Now what I want to do is compare that to what happens if we do allow for localities to adapt. And then we see that the 50% increase in storm severity leads to about a 28% increase in damage instead of the full 47% increase in damage. So adaptation is considerably reducing the increase in damage that we get by about 45%. So then what we kind of care about is, well, what does this mean for welfare? And so to measure welfare, we use something called the consumption equivalent variation. So think about this as your percentage increase in consumption you would need in every period of today, in our kind of baseline economy, so that you're indifferent between living in our world today versus living in one of these counterfactual worlds, which are our climate change worlds. So negative numbers here indicate that climate change makes you worse off. You would have to take consumption away from people today in order to make them indifferent between living in our world today versus living in one of these counterfactuals. And so all these numbers are negative, so climate change makes us worse off, as we would expect. And they also get more negative as the severity gets more severe, which you'd also expect. I think the more interesting lines of the table are comparing that no adaptation and the adaptation growth. And there you see that adaptation is reducing the welfare costs of climate change by about 15 to 20%. Now that's smaller than that reduction in damage. We saw before adaptation reducing the damage by 45%. What we have to remember here is you have to pay for this adaptation capital. It doesn't come for free. So we're going to get bigger implications for damage than we'll get for welfare. Okay, so that's it. Kind of what we've done here is look at the implications of federal disaster policy for adaptation and also the effects of adaptation on